could you provide a bit of an overview of the actuator design and kind of how it works and benefits it offers in this application?
Sure, actually, it's a pretty simple design. So the difference, and we'll get into that maybe a little later, is this is an inline design. So what we mean by an inline design is it's just a single tube which we implement the electrical side. We have an electrical side and a mechanical side to the actuator. And the inline design provides the benefit of being able to seal better than, say, the alternative type designs out there. So in this case, when we were developing, we knew that we had to deal with a lot of environmental issues as far as different temperatures, climates such as high humidity, high heat, cold. And so one of the keys was to develop this actuator and make sure that the components were very robust and corrosion resistant. So the actuator inline design, like I said, we break it down into two sections. The mechanical section just has a bearing housing with a drive shaft. That drive shaft is coupled to a lead screw, and the lead screw drives a nut that's attached to what we call a thrust tube. And so the thrust tube, once the screw turns, moves in and out of the aluminum housing of the actuator and generates a thrust force, or actually what is used to pivot the panels. And then on the other side of the actuator, we have what we call the electrical chamber. And this is where the motor and gearbox and all the position feedback is supplied into driving this actuator. And so it's very important in this side that everything is sealed and maintained in order to keep contamination or moisture and things like that that can deteriorate the actuator. Basically, our design is made out of a high strength aluminum for the housing and a high strength aluminum for the thrust tube. And what we do is we add a thick layer of anodization because we know that over time UV exposure and elements can break down the coatings, and then you can get corrosion issues as well. So by providing this thicker anodization coating, we can get a much longer corrosion resistant free life of the actuator. So each side of the actuator, the one side of the actuator is what we call a trunnion mount. It's a sealed cap that caps the motor in, and then the opposite side is the fixed mount that ties to the frame of the solar actuator frame. And it actually has a signal that can be provided to the controller of the solar field so they can determine where the position of that panel is in relationship to the sun.
And so what technologies are there, other technologies built into that controller, or is it like software or to help with that, or?
Well, those are actually, in this case, was dictated by the existing solar farms. So that was one of the biggest challenges we had, is that this actuator had to fit, form, fit, and function identical into this existing system. And so I think the challenges were that we had to know what the strokes were, what the envelope size was, what type of feedback signal did they need in order to control the actuator. The other things were end of travel limit switches for retract and extending the actuator. And so all of these things had to come together in order to be able to provide a replacement that you could plug in, hook up the existing connectors, and they could hit their button and they could go. So in this specific design, we had to take all of those things into consideration, and we had to make it robust. And to add on top of that, it had to be very cost effective. So, you can design an actuator that, for if you have enough time and money, you can design a really high-end actuator that can do almost anything. But there is a cost constraint just because of the volumes that we're talking about, and the fact that we have to make it corrosion resistant, weather resistant, and also protect against moisture. One of the things we did find out is that you can protect it against rain and dust and things like that and provide the adequate sealing for it. But there also is the variations in temperature and humidity that can cause condensation to build up inside of the actuator. So we also had a solution for that. Is what we've done is we've added breathable valves to both the mechanical and the electrical side, so that when we do get these conditions where we get condensation in, The moisture has a pathway out of the actuator, but yet there's no pathway for the moisture to get into the actuator.
And so when you were mentioning before some of those challenges that, with designing it, did you work together directly with the customer to then kind of help overcome and make sure the actuator could meet all those specifications and fit the existing form factor, or?
Sure. So one of the things when you're dealing with an energy company and they're running the solar farms, they don't have a lot of ties. Well, they have ties back to the original manufacturer, but what we find out in this industry is that at the very beginning there was a lot of players for the installation or integrators of these
Mm,
solar farms, and a lot of those companies are no longer in business.
mm,
And so some of that information or baseline for what is required was not existent. So we
mm,
actually had to work with the energy company, visits to the solar field, examining their existing systems, how they were controlled, what problems were they having, and coming up with a solution that would be a robust design, and do some testing in-house. We did some very thorough testing to simulate multiple years of loading and environmental conditions such as moisture and hot and cold and things like
mm,
that, so we could get the best idea on simulating those environmental conditions. Um, the other thing we did is we also had some prototypes that we put out into the field, and we ran them for a year and a half and took a look at and broke them down to see um, how they functioned in those environmental conditions, and we had very good success in that
mm,
aspect. So as far as challenges, yes, it was almost like a reverse engineering
mm.
exercise, but trying to implement the best solution for that customer.
And so, how does the Schaeffler inline actuator design differ from, those that were previously used on some of these solar tracking systems?
The typical actuator you'll see is what we call a parallel design. And
Okay.
so what a parallel design is it has a motor that is external and it runs parallel to the tube of the actuator. And so the motor actually is coupled through, either it could be a belt drive system or a gear system or a gearbox. And then that gearbox it's like a 90-degree and actually drives the screw from that. So a parallel is motor sits on the outside, it runs parallel with the tube of the actuator, and drives the actuator via a gearbox. Now, one of the issues with that is that this motor is exposed externally, so it's exposed to the elements. And also because it's not just a round tube, you have a lot of collection points, and that water or dust or deterioration through UV exposure that can cause water ingress, or like I said, again, condensation getting in with really no way to escape the actuator. So what we found is that by going to the inline design, everything is encapsulated inside a tube and can be very well protected. The only downside of that is it does take a little bit more design space,
Mm,
because we have to implement the motor and gearbox system within the same tube.
mm.
So again, another challenge we faced, but we were able to overcome that, and be able to work with the customer and be able to implement it even with those extra links that we had to deal with.
Great. Well, I think those are all the questions I had for now. I really appreciate you being able to take the time to provide some insight on this inline actuator and its use in solar tracking and other applications.